So today's lecture is about locality sensitive hashing. So this is, again, continuing on the theme of last lecture. This is kind of geometric setting. We'll be talking mostly about high-dimensional geometry. And this is kind of converging on the topic of hashing, though it is a little bit different type of hashing than perhaps other lectures. It will be geometric hashing. Anyway, we'll go there. Okay, and again, kind of the problem, the focus, right, of attention is this problem called nearest neighbor search that I defined yesterday, which is a data structure question, where for the query we need to report the closest point from a data set. Okay, and so we'll be designing more efficient data structure for this nearest neighbor search, but as I mentioned yesterday, kind of the exact version is a hard problem. Usually everything becomes exponential in dimension, and basically to alleviate this issue called curse of dimensionality, it has been proposed to study the approximate version of this problem. And this is the approximate version of this problem will be where we can state and prove results, theoretical guarantees. Okay? So let me define this approximate version so that we're on the same page. And before that, I'll actually define not an approximate version, but I'll define what is called threshold version, where not nearest neighbor, but near neighbor. Okay? In the near neighbor, we're given a threshold r, small r, and essentially, the question is to find the point within distance r, right? So, for example, for a query point Q, we're okay with any point in this block. Okay? However, is not the answer. So this is, so far no approximation, just near neighbor. So now let me define what is the approximate version. So C from now on will be approximation. Think of C like 2, for example. And what is the approximate version? Basically, we introduce this gray area, where in some sense, things may or may not happen. And formally, the definition is as follows. So we need to report any point within this bigger ball, CR, say 2R, as long as there is some point in this smaller ball. Okay? So if there is some ball, so there is a point within like in smaller ball, but where the data structure is relaxed to output something from a bigger ball. If there is nothing inside, then the data structure may or may not report something in this bigger ball. So put it differently, this gray area, where I guess it's more yellow here, is kind of data structure has freedom whether to consider points that live there or not. Or put differently, if there is nothing in this gray area, so it happens that your data set is such that there is nothing in this gray area, then the data structure will actually return the exact near neighbor within threshold R. Right? And all the algorithms will be randomized. We're using hashing, right? And a point P, approximate point, will be returned with 90% probability, let's say. Right? Okay. And let me mention kind of one way this is used, especially in practice. It is essentially a heuristic for exact nearest neighbor. The idea being that usually the data structures will return a bunch of points, basically a list of candidates. These candidates will include most of the points inside and may include some points in this yellow band. So if the yellow band doesn't contain too many points, then the list is not too large, and the list is guaranteed to contain your exact near neighbors, and then you can post-filter, essentially. So think about this algorithm as a very good filtering algorithm to reduce your search space of potential answers. Okay, and this is often how it is used in practice. Okay, so finally we're talking about hashing, locality sensitive hashing. So what is so we're talking about algorithms for this problem, for approximate problem, and essentially all the algorithms I'll be talking about are based on locality sensitive hashing, and essentially all all theoretical algorithms for this problem that achieve sublinear query time are based on locality sensitive hashing. Okay, so what is locality sensitive hashing? It is a hash function. It is based on a random hash function, G. But I mean, it is defined on real space of dimension D. So this is our space where we solve our nearest neighbor search. Again, dimension D can be potentially large. Think about this as like 700, for example. And we want the following properties from this hash function. Namely, I mean, there will be two properties that we want. It works for close, and basically we partition kind of in these two regimes. One is we define the regime close when the distance between points is within distance R. So this is, think about this, in points within this smaller ball. And far is when the distance between points is bigger than CR. So this is outside the outer ball. So basically we don't have guarantees for this gray area, but we have guarantees for inside and the bigger outside. And what do we want? Essentially what we want is that it is a hash function such that if points are close, then the probability of collision is high. And if the points are far, then the probability of collision is small. Okay? So it is, to kind of draw parallels with normal hashing, in some sense, the far regime is, roughly what you want from a normal hash function as well, but, the points are unrelated, then they shouldn't collide, right? And this is what we want from a hash function. But there is a difference that the points that are actually close, we want them to collide, actually. Okay? So this is slightly different from kind of standard hashing, where you say, like, as soon as points are slightly different, they should not collide at all. Here we actually require that the points, if they are somewhat similar or close, they should collide. Okay? And there is this kind of threshold effect, right? And, and now what would be the... So first of all, you should, one equivalent perspective on this hash function is that it induces a space partition on the entire space. So this green blob is this d-dimensional Euclidean space. And if you are curious how a d-dimensional space looks like, right? So a hash function induces a space partition on this space. So by space partition, this is a space partition, right? Where each part, so for example, this part is the locus of points that have exactly the same hash value under this hash function G. Okay, so it is a randomized space partition, right? And sometimes it will be useful to think about this hash function as a space partition. So now, if we were to have these guarantees, and suppose this high is kind of almost 1, this small is essentially 0, what would be the data structure for nearest neighbor search? It's a question for the audience.
Voronoi diagram.
Excuse me?
Voronoi diagram.
So Voronoi diagram, okay, I mentioned this last time. Voronoi diagram for in this situation will take space which is n to power d roughly.
Of course, yes. I thought you said with no post bar.
No, suppose we have this function g. Right? We have suppose this function g, which is this high is essentially 1, this small is essentially 0.
You just use chaining.
Sorry?
Chaining. You just
Chaining.
The thing where you just look in the bucket of the things with the same hash value.
Yeah. Yeah, basically it's just a hash table. Right? Yes, you're right. So basically we just take one hash table, we put all the data set points according to this function g into this hash table. I guess there is a minor issue that where does the function g maps to? Maps to some discrete universe, and you can use, say, universal hashing to map it down to a hash table. So use kind of standard hashing that Mika was talking about to map it down into a table of size, I don't know, 10n, for example. And then at a query point, so a query point arrives, we just look up the bucket where the query point Q lies in. And by these guarantees, this guarantee says that we'll find our near neighbor. This guarantee says that that bucket will not contain any other points. Okay? So this is correctness, and this says that the query time will be very small. Question?
Yeah. These constraints, they're not kind of like fighting each other. So you have another clause, which is the first one is distance R to the second, which is distance R to the third. So and then you want them there to be
Absolutely, you're absolutely right. I mean, yes, this is an ideal situation, and naturally they are fighting each other, right? And finding a trade-off between them will be, the point of the entire lecture. You're absolutely right. So, another question, yeah?
Who gets to choose the C?
Sorry?
Does the user choose the C or the data structure?
Good. So C, the approximation, let's say we fix it in advance. Suppose we are looking for a 2 approximation. I'll mention a little bit later how, say, in practice you choose an approximation C. But, think about now as we fix C to be 2, and that's it, right? Okay. So now, the first question was about that, these things fight actually, right? I mean, there will be, for any space partition, there will be a border and there will be points near the border which will be cut, right? So this is not achievable. So achieving exactly this threshold high and small is not quite achievable. What we'll settle for is something like that. So we have probability which is not so small versus something which is small. Okay? But there will be some gap. And quantifying this gap, will be the point of, most of the rest of the lecture. Okay? So pictorially, we'll have a hash function where if we draw the probability of collision of the points as a function of the distance, it will be some decreasing function. And we want this function to be essentially as sharp as possible. Right? And it will be, this is what we'll be talking about. And in this situation, when we have this not so small and small, we'll have to use several hash functions. Because maybe one hash function will fail to find the near neighbor because this probability is not high enough. So we'll have to repeat this experiment a few times, basically construct a few of these partitions. And we hope that in one of the partitions, for example, in this third one, we'll finally have that the query point and desired point will collide. Okay? Now, how many hash functions do we use? N to power rho. What is rho? So rho will be a function of these probabilities. So let me call probability P1 this probability of not so small. This probability P2 probability of collision of far points. Pictorially this is this point P1, this is point P2. Rho is this function. So at the moment it looks like something not quite comprehensible. We will get there why this is the right answer. Right? But essentially the point here is that we'll use a number of hash functions. The number of hash functions is n to power some constant rho. Rho will be a function of the approximation, right? And it will essentially depend on how well can we what is the threshold between, what is the gap between these probabilities P1 and P2? Okay? So this is, this is kind of a general scheme. Now, the idea is that, okay, so what are the hash functions, right? What are these locally sensitive hash functions? So I'll give you an example now. So before I go to example is, one operation that we can do is we can concatenate these hash functions, right? And kind of in usual way. So usually this hash function G is obtained by concatenating several primitive or very simple hash functions. So essentially this is how it looks, right? A hash function G will be composed of a few of K in particular more primitive hash functions. And just to give a very concrete example, suppose our space, so we are working on nearest neighbor search in Hamming space. Okay? So say not Euclidean, but Hamming space, and this is what we care about, and it is d-dimensional Hamming space. So here is the simple primitive function that we can use. In particular, hash function for a point P just projects on coordinate J, where J is chosen randomly. Okay? And it should be intuitively obvious that this hash function, the probability of collision of 2 points P and Q depends on the distance between P and Q, or Hamming distance. If the points are mostly different in all the coordinates, then choosing a random coordinate will probably give a certificate that these things are different, right? They will not collide, as opposed to if the points are very similar to each other, then many coordinates are similar, so then choosing a random one will give us a bigger probability of collision. Okay, so continuing, this kind of global function, hash function G, is just a concatenation of k bits, k random bits, chosen at random. And so this fully now describes the algorithm. I mean, except for choosing the parameters, at least the algorithm is fully described. And let me compute what parameter rho do we achieve in this situation. So first of all, under this hash function h, the probability of collision under this function h is something like 1 minus Hamming space between p and q divided by dimension d. Right? Simple, like, what is the probability that we choose exactly the coordinate where they're different, it's exactly Hamming distance divided by dimension. And now you can compute the probabilities of, what is the probability of collision when the distance is at most r? It is this, right? 1 minus r divided by d. And I'll use some approximation that 1 minus r divided by d is essentially equal to e to minus r divided by d. At least for if dimension d is much larger than r, this is a faithful approximation. Okay? Yes?
What is the parameter R?
So r, I mean, again, we are solving r near neighbor, so we have point query q. This is r, and we have to find near neighbor within distance r, and we have this bigger ball of radius cr, right? So this is essentially the near neighbor here, but we don't want to report anything here, and this is the gray area, right? The shell. Okay, so the same computation for P2. So the P2, again, is probability of collision for points that are far, a distance at least CR. And again, using this approximation, this is essentially equal to d to minus CR divided by d. And now you plug in these probabilities P1 and P2 into rho, and you get essentially 1 over c. Okay, so the exponent, say for approximation c equals 2, will be a half. So the number of hash tables that we need to use will be root n. Okay? Okay, so just to repeat the entire algorithm again. So again, we use data structure where we have what we call n to power rho hash tables. Each hash table uses an independent hash function obtained as a concatenation of these primitive hash functions. And each hash table just takes all the points, uses this hash function, maps into a hash table. At a query time, we go over all the hash tables, look at the buckets where the query point Q is hashed into, and retrieves all the points here, and as soon as it finds an approximate near neighbor, basically an OK answer, it reports that point, and we're done. Okay, and just, very quickly, at least the space and the query time guarantees should be immediately obvious. Namely, we have L tables, so the space will be, there is order n space per table, per hash table, we just hash n points in there. So it will be n times L, which is n to power 1 plus rho, plus the space to store points, for example. And the query time is essentially L, the number of hash tables, plus, I mean, this is perhaps not obvious, but we will prove, plus the time to hash, which is usually about k, and we have to go through all these to compute all these hash evaluations, plus d to compute the distance to the points, to the candidate points, and essentially it will be n to power rho times, let's say, dimension d, an expectation. So I mean, we'll prove that this query time is indeed this, but at least for the query time will be composed of computing the hash tables and looking up points and iterating through all the points in the buckets that we found. Are there questions about the algorithm? Yes?
You did the analysis just for H and not for G.
Sorry?
You did the analysis just for the H and not for the G, which was the concatenation.
the raw calculation is exactly the same for functions h. Sorry, again, lost the chalk. The calculation for h and for g are exactly the same. Where is it?
It's on the same hiding place.
Same hiding place.
Oh, right here again. No, it's a different one, but that's fine. It works. Yeah, there is a longer one. So let's say this P1 is the probability of collision under let's say P1 of H is the probability of collision under H, right? Then if G is a concatenation exactly of K of these functions, right? Then P1 of G basically when P1 of G will be exactly P1 of H raised to power K. And the same of P2. So then raw computation for G will be the same as basically log of P1 of G divided by log of P2 of G. And this is exactly equal to K times log of 1 over P1 of H. K times log of 1 over P2 of H. So this is, and before this K disappears, so this is exactly the same calculation for H or for G. So basically, this contrast between probabilities is independent of whether we concatenated a few hash functions or not. Okay, so let me do an analysis. Oh, I found the job. So let me do analysis of LSH schema, and it will be clear again why this is the case. So first of all, how do we choose these parameters K now? So I'll try to prove that this always works, right? To give full details actually. So we use again just how did we choose this n to power rho, and how does this rho show up in the picture, right? This is what we're trying to do now. So we have these parameters K now. We have to choose them somehow. So we have these L hash tables with these functions. So suppose we have, let's fix one hash table, and we choose this function G, and let's say suppose P1 and P2 are the probabilities of collision under one primitive function H. Right? So if we repeat, if our function G is a concatenation of K of them, then the probability of collision of R points is raised to power K, and the probability of collision of a closed pair is also raised to power K. Okay, and now, I guess pictorially this is how it looks like. This is collision probability on this axis, this is the distance. And, that would be the graph, say, of probability of collision for K equals 1. So if we raise it, if we concatenate two of these functions, I think this is, if it is collision under two hash functions, then it drops. And right, we raise it squared, so these are numbers under 1, so it drops, right? The idea being that this increases so this will be P1 squared, this will be P2 squared, right? The contrast between these increases more, and the ratio between these probabilities. And what do we want? How do we set? We have a choice of K now. How do we set this K? So we set K such that this P2 to power K is equal to 1 over n. Okay, why do we want to do this? So this will be one hash table. There may be many far points, up to n far points. We want that these far points do not collide with our query point. Okay, so this is why we'll make the probability of collision of a far point and a query to be equal 1 over n. So with an expectation, we have at most one far point colliding in our bucket. Okay, so this is how we set K. Now you can compute, now that K is fixed, the ratio, the relation between P1 and P2 is given by rho. We can exactly plug in K and see what we get. And we plug in K here. So show this calculation once. Basically, rho was defined as basically log of 1 over P1 by log of 1 over P2. This is equivalent to saying that P1 is equal to P2 to power rho. Okay, if you take log of both sides, then this is exactly what rho is, right? So you plug in, you plug this rho here, and this is what you get, right? Because P2 to power k is equal to 1 over n, so you get 1 over n to power rho. Right, and this is how you get rho, right? I mean, this is why the definition of rho is what it is, right? Exactly this calculation. And now, if you have the probability of collision of close pair something like 1 over n to power rho, you know, rho is something like a half, for example, then in your one of the hash tables will succeed in finding a near neighbor with probability 1 over root n, so you have to repeat roughly 1 order of root n times to succeed in at least one hash table with constant probability. Okay. So, and yeah, this is where rho comes from. This is kind of more formal correctness guarantee. So, more formally, let's say, so suppose P star is the R near, this should be small r actually. So P star is near neighbor, right? So it is a point inside this smaller ball. So the algorithm fails if this near neighbor P star does not appear in any of the buckets, right? And probability that it doesn't appear in any of the buckets is something like at most 1 minus P1 to power k. Probability that it doesn't collide in any of these n to power rho hash tables is at most this one, right? I mean, this is exactly the calculation that says that you need to repeat n to power rho times if each event succeeds with probability 1 over 1 divided by n to power rho. Okay? And the runtime, I'm just repeating essentially what I said on the previous slide. So the runtime is composed, so the query runtime is dominated by two parts, right? One is hash function evaluation. So we need to compute these hash functions and then go into the corresponding buckets. This is part one. And part two is that once we go to the buckets, these buckets can have a lot of points. We need to iterate for those points. Okay? So, and iterating basically means computing the distances to both points. So what we care about, so in the algorithm, once we go through the buckets, if we find the near neighbor, so something within distance r, so we are great, we really found what we wanted. We find something approximate near neighbor, so within distance, say CR, then it's also good. I mean, this is the guarantee of the algorithm that will return an approximate near neighbor. And so what we care on about is how many far points do we encounter in all the buckets. And essentially, you know, this is why we set up P2 to power k to be 1 over n, so that in expectation we have exactly 1 point per hash table, 1 far point per hash table. And basically over L hash tables, the expected number of far points is L. And you know, you can compute exactly what happens, and this will be roughly the runtime if you plug in the numbers, at least for the Hamming case. Okay, so I mean the point being, so you know the algorithm is like really simple, but you mostly compute hash tables. All that the algorithm really depends. I mean the main parameter of the algorithm becomes this parameter rho. I mean how good of a rho can we obtain, right? And at the moment for the Hamming space, I showed you that you can obtain rho equals to 1 over c for Hamming space. Okay, so for approximation 2, this means that you get actually something of the sort root n query time for root and hash tables. Okay, so then there is a question. Okay, can we do better? I mean, are there better hash functions? Are there better space partitions? And it turns out that for Euclidean space you can do better. Okay, you can design better locality sensitive hash functions. So this is what we're going to do. So first of all, I'll show you one other construction.
And for Hamming distance,
Yeah.
are there better hash functions for Hamming distance?
I will get there. The short answer is no. The long answer is yes. But I'll get there, right? So for locality sensitive hashing, 1/c is optimal. But I'll get a little bit later in lower bounds on what exactly they mean. Okay. So let's talk about Euclidean space for the moment. So for Euclidean space, you can design better hash partitions, space partitions, basically better LSH functions. So let me design a scheme that does not obtain much better guarantees, but it's a little bit different, and it will lead on to the next construction. So again, do the computation of primitive functions. What are these primitive functions? Again, this is our d-dimensional space, if you remember. What we'll do is we'll pick a random line, quantize it, project the point onto this random line, and this will be our bucket. Okay, so this is really equivalent to random dimensionality reduction into dimension 1. And as we showed yesterday, this projection kind of, in approximate sense, preserves the distance between points, right? So after we quantize, we expect that the points that are close will be closer on this line and will be less likely to be cut by these borders, essentially. And if the points are far away, then the distance on the line will be probably larger, and they are more likely to be cut by these segments, essentially by this border between segments. Okay, and this is formally how one write this hash function. So it will be point P projected onto line L. W is just scaling plus B. This is the shift on the line, and then you take floor operation to quantize it. To transform from real into an integer. Okay? And L will be a random Gaussian vector, B is a random shift, and W is a parameter for R. It's related to the threshold R that we are looking at. So this is the hash function, and just to go back to the notion of space partitions, this hash function corresponds to this space partition, right? All the points in these slabs have exactly the same hash function, right? And just to understand, so this is a hash function H, right? So how does a hash function G look like? So this is a repeat of this procedure a few times, right? In concatenation. So this means that you do, for k equals 2, this will be the space partition of the function given by function G, right? So again, you take another random line, you quantize it, and roughly what you do. So basically what happens is that in the end, you'll take your space, you partition into something that looks like cells. Okay? And this is the bucket of the point P. And I won't go through the calculation, but you can prove that essentially for this hash function obtains rho, which is also equal to 1/c. Okay? Roughly the same as for Hamming space. Okay, so for Euclidean space you can do better, and basically now I'll show you what is essentially an optimal LSH for Euclidean space, and it will obtain rho which is equal to 1/c squared. Okay, so basically again for approximation 2, this will be n to 0.25 Copenhagen as opposed to root n. Okay. And how such LSH works? Okay, so this is roughly how the partition. So the previous, the one that I showed in the previous slide, roughly partitions the space into these cells, right? Into regular grid, and you can think it's like it partitions space into these parts that look like cubes in high-dimensional space. Right? So the idea is that cubes are not particularly good space partitions for Euclidean space, and it's better to partition Euclidean space into balls, essentially, right? So the idea is to really replace a regular grid by a grid of balls, right? So something of that sort. This is roughly what we want to do in Euclidean space. This is how we want to partition it. The problem is that a grid of, so at point P, it falls into ball, this will be its bucket. Right? Now, the problem is that the grid of balls, ideally you'd like to tessellate, partition the space into balls, right? In high dimensional it is called tessellate. Again, if you want to impress your colleagues, right? Fancy words. The problem is that already in dimension 2 it is not possible to partition the space into balls, right? And in high dimension, it actually becomes harder and harder. And in fact, however you pack the balls in a high dimensional space, you will cover an exponentially small part of the space actually. So if your point P is random, it will most likely just hit empty space, right? Which is not assigned to any ball. So what you have to do is essentially repeat this procedure a few times. So what is this procedure? As they say, picture is worth 1,000 words. So let me show this procedure in two-dimensional space. So what it will show, you throw at the space a lot of grids of balls, and they have an order, and basically you will carve out the remaining space as much as possible. So all these green balls are separate parts, or parts of the space partition. When you throw another grid of, say, red balls, they carve out the remaining parts of the space. Then you throw maybe another set of a grid of blue balls, and so forth. And you continue until you've covered the entire space. You don't see the colors well, but okay, so this will be the partition, right? So every green ball or every kind of magenta part will be a separate part of the space, right? So this is how a partition looks like in two-dimensional space, and in high-dimensional space, you can imagine. So when we're generating these pictures, actually, for this paper, we try to do this in three-dimensional space. And it looked like very nice, these balls, and kind of how we carve out the space, except it started looking a little bit too psychedelic, so before the two-dimensional space actually looks a little bit better, right? Anyway, so how many grids of balls do we need to do this to cover the space? It turns out that many. And this many is exponential in the dimension. Yes?
When you do these balls, won't you have overlaps so you can have a point in several balls simultaneously?
Right. Good question. Yeah. So there is overlap. There will naturally be overlap. We cannot tessellate. So for example, once we've thrown these green balls, right? So this is the first grid. When we throw the second grid, so the part occupied by this ball is only the part that has not been occupied before. So in some sense, you have an order on these grids, and the point will collide in the first ball in this order, right? Which contains it. Yeah.
If you're already repeating this a few times, why don't you just take larger balls?
You want the small distance.
It would be overlap, but you're overlapping anyway with these balls, right? I guess the carving is really important.
Yeah, so there is a question of what if you have two of these green balls overlap? What are the semantics of this now?
So at least, you have to, you move the exponential problem into the query time, right?
At the moment, yes. Yes, you're right. So if you have balls that are larger, they begin to, even these green balls, they begin to intersect. And there is a question of semantics, what do you do if these balls intersect? Right, either you can push them to be so far that they intersect a lot, actually. If you want to do this a few times, right, and not repeat too many times, these balls will have to intersect a lot.
Yeah, so if you just use larger balls, it's
so what?
It's doing the same thing as.
So the question is, what do you do then, right? Do you, so if you have two balls that are intersecting, do you put an order on them, or do you cut them through the median?
Same thing you do here.
So what this means, these green balls are all thrown at the space at the same time, and since they don't intersect, there isn't a question of order between them. If we throw these balls one by one,
and the next set of balls?
So,
Compared to this layer?
so there is one layer, and the second layer has order 2 now, right?
Okay.
So different colors have orders, but the same colors do not have order between them. If we introduce order between the same color balls in this situation, right, and they are ball and they are intersecting, then you have the same problem. You'll need to throw an exponential number of
It's
balls.
essentially the same thing.
Yeah.
Okay.
Yes, question?
How, hexagons,
Sorry?
hexagons, I have a nice
Great, yeah, in two-dimensional space, this is actually a very good approximation to tessellating with balls. I agree. So the question is how to do this in high-dimensional space. What is the equivalent of hexagons? But yes, I mean, this is, that's a very good point. Another question?
Yeah, couldn't you just make the balls touch? Like if you don't have any space between the green balls?
You can make them touch, yeah. It's just that the proof is slightly easier if they don't touch. And it doesn't, I mean, except for certain constants, it doesn't change things too much. But yes, you're right. You can. Okay, so we need too many grids of balls. So actually, the number of grids of balls that are needed here is exponential in the dimension d, right? So if our hash function takes exponential in dimension kind of information, it's again bad, right? I mean, we wanted to avoid exponential in dimension situation. So what we do is that we, before doing this partitioning, we actually project the space into dimension t using, say, Johnson-Strauss, and doing this partition in this lower dimensional space t. This is how it looks like. So point p will be projected into one of these balls. This is the partition. And one can prove that in this situation, rho will become 1 over c squared. Okay, which is an improvement over Hamming space where this exponent was 1 over c. And I mean, there is a question of choice of this reduced dimension t, and this dimension t is a trade-off between two things, right? Resolves your question like, okay, if I reduce the dimension t, why don't I put it at one of the extremes, like the original dimension t, d, or t equals 1? No, for t equals 1, this really corresponds to the hashing that I explained in the previous slide, where we just project onto a random line and partition it into the segments. This is really essentially equivalent to that, because balls in one dimension are really segments. Okay, so in general, we'll choose dimension t, which is a trade-off between two things. One is the number of hash tables. So rho is equal to 1 over c squared plus some function of t, some decreasing function of t. Right? So for constant t, this will be some small constant, but as t grows, this becomes smaller and smaller. Okay? And I mean, if you're curious what it is exactly, it is something like 1 over root t, this small of 1. And time to hash, because time to hash, I mean, at the moment at least, right, there is no other better way to hash than essentially to iterate through all these grids of balls and find which is the first grid of ball that captures my point P. Right? And the number of grids to cover the entire space is exponential in this dimension t. So the time to hash will be, the number of these grids, which is t to power order t. This is the number of grids that we need to throw to cover the space. Okay, and you choose some t that optimizes this, right? And, so the total query time becomes something is d times, so dimension times n to power 1 over c squared plus some small one. Okay, so this is the scheme. And on the next slide, I will show you a proof intuition why this scheme achieves 1 over c squared. And I mean, in some sense, it will use Euclidean geometry in an essential way, because we can obtain better things in Euclidean space. The questions? No? Okay, good. All right, so proof idea. So we need to prove that rho is equal to roughly 1 over c squared, which is equivalent to saying, so let's define P of R to be probability of collision for points at distance R, right? So again, kind of, rho is defined here, right? So what we need to prove is the probability of collision for close points is at least probability of collision of far points at distance r to this power 1 over c squared. this is what we need to prove. You know, this is what it means for rho to be 1 over c squared. Okay. So we will some pictures. Oh, by the way, the proof finishes here on this slide. I mean, it will not be too long. On the same time, it's intuition. Okay, so consider some points. So really, what we'll just compute, we'll compute an approximation to this probability PR, and we'll notice that this happens. This will be kind of the situation. And how do we compute this probability of collision for points at distance r? So we have points Q and P. And now, first of all, so we did this dimension reduction into dimension T. So if dimension T is sufficiently high, kind of high constant, very high constant, when the distance between P and Q will be preserved, right? This is what we proved yesterday. And notice that yesterday we were talking about endpoints, and this is why the target dimension that we wanted to argue about was log n, right? So the type of dimension reduction, normal Strauss would talk about endpoints and say we need to project a dimension log n, and this will preserve all the distances. Here we really care about kind of 2 points, right? This is how the LSH analysis works. I mean, what is the probability of collision of 2 points? So in some sense, we really care only about 2 points. This is not completely accurately, but intuitively this is true. So it is okay to reduce into a very high dimension T, but constantly. Okay, this will preserve the distances between P and Q approximately. And now let me argue how do we compute this probability of collision. So kind of going back to how these hash functions are chosen. Let me draw. So these, like I didn't mention, but these balls have some radius. Let's call this radius W, right? So let me draw balls of radius W around P and Q. So these are the 2 points whose collision probability we are trying to compute. And the idea is that, well, we need to try to understand what is the probability that these 2 points fall into the same ball of a grid of balls, right? So if the centers, so let me think about the point, the center of the ball corresponding to this hash function being chosen randomly in this space, right? So if this center is sufficiently far away from these points P and Q, in particular it is outside this union of these 2 balls of radius W, when it does not affect whether P and Q have collided or not. Right? So as long as the center is outside these 2 balls, we have, I mean, the event whether P and Q will be colliding under this hash function or not has not been determined yet. It does not affect it. However, as soon as there is a center that falls inside the union of these inside 2 balls, it will determine whether points P and Q collided or not. In particular, if this ball captures Q but not P, meaning it falls in this ball, in ball around Q but not the ball around P, this means that P and Q will not collide. Right? On the other hand, if this center falls in exactly the intersection of these 2 balls around P and Q, in this intersection, then this event will say that this particular ball will capture both P and Q. So P and Q will collide. All this discussion just says that the probability of collision of P and Q is exactly equal to the intersection of the 2 balls around P and Q divided by the volume of the intersection divided by the volume of the union of these 2 balls. Okay? Okay, some animation. So now we need to compute this. I mean, so what you can do is, you can go to math books and like pull out what is the volume of the intersection, volume of the union of hydrogen balls. Actually, these things are somewhat hard to compute and you can approximate, but I want to give you the intuition how these formulas look like. And basically, so let me take this ball around Q. And the probability, the volume, roughly the ratio between the volume of the union of the intersection of these two balls divided by the volume of the union of these two balls is roughly equal to the volume of this cap divided by the volume of the entire sphere. Okay? This is a very good approximation to the quantity that we need to compute. And what is the probability, what is the ratio between the volume of this cap divided by the volume of the entire sphere? This is exactly equal to the probability that a random point chosen from the sphere goes beyond this line, is to the right of this line. But this is a very good approximation to a probability of collision, to P of 9.
Why is it exactly the probability of collision?
Because it is not quite true that the intersection divided by the union of these two balls is equal to the volume of the cap divided by the volume. So it's because it's volume of the union as opposed to twice the volume of the ball. Okay? But since, I mean, numbers that we'll be getting are very small, I mean, the volume of the union is equal to the twice volume of the ball minus the volume of the intersection, right? But the volume of the intersection will be very small, so it doesn't matter, like plus minus. So this is a very good approximation. So now we need to compute what is the probability that a random point chosen from the sphere goes to the right of this line. Now, yeah, this is a random point. So here comes the linear geometry part. Is that one way to choose random points from a sphere is just to choose a point from a Gaussian distribution, from multidimensional Gaussian distribution. And if you remember, Gaussian distribution is centrally symmetric, the distance will actually concentrate, so it is really equivalent. So then it remains to say, like, okay, we have point U, which is chosen from high-dimensional Gaussian distribution, which means that each coordinate is chosen from Gaussian distribution. What is the probability that it is beyond this line? Well, I mean, this line, this coordinate, this axis x is just one direction, right? So it's the question that, this in direction x, the coordinate of u is bigger than some value. So this is really can be computed from the Gaussian distribution. It's really just the tail of a Gaussian distribution, and it is exactly roughly equal to exponential minus some constant. But the most important part is that it is r squared, right? So this distance between here and here is r divided by 2. So up to constants, which will hide in this big A, the probability is exponential in minus r squared. And this is really the important part, right? This square here in the exponential distribution is where we'll get 1 over c squared as opposed to 1 over c. So then, you plug in the numbers, and so probability for distance r will be something like exponential in minus a r squared. And for, if you are to replace r with cr, then you'll get c squared in the exponent. Okay, I mean, this is the exact calculation, but the real intuition is that c squared comes from the dependence on r squared in the exponent for Gaussian distribution. Okay, and this is the entire proof. Okay? Are there questions about that? So this is the way it will be kind of from now on, the rest of the talk will go at a higher level a bit, and not just to show kind of a bigger picture of what's happening. Yeah.
So you maybe give even more intuition about what goes on in this proof. In what sense is the ball better than the cubes that we had before?
So here is one. So some of these things are called basically isoperimetric questions, right? So the idea is here is a question that is a classical question in linear geometry is that imagine I give you a budget of volume. You have to construct a body, a part kind of the space with volume equals to 1. And I ask you to construct an object that minimizes the perimeter of that object, right? And there is a classical theorem saying that the object that minimizes the perimeter for a fixed volume will be a sphere. Right? And LSH, I mean, basically this gap between T1 and T2 is not that far from this kind of question. Right? So for a fixed volume roughly corresponds to fixing the probability T2 of collision of far points. And the perimeter corresponds to the probability of collision of very close points. So imagine when we take C, the approximation, to tend to infinity, this means that we're looking at close points for us means to be very, very, very close, right? And then we throw essentially kind of these 2 points that are very, very close into the space. So the probability that they do not collide is exactly kind of the perimeter of our space partition, right? So it is very related to this kind of isotropic questions.
It's a good answer.
Okay. All right. So this is what we have, and now. Okay. So yeah. So actually, I mean, there's a bunch of kind of LSH functions that have appeared in meanwhile, right? And actually, so some of them. Yeah. So some of them, as I mentioned yesterday, before I go there, as I mentioned yesterday, we want to solve nearest neighbor search under different situations. We have usually these high-dimensional points are embeddings of different objects like documents or music snippets, right? And for different objects, we might want to embed them in different or place them in different spaces, Euclidean or Hamming or more complicated like eddy distance. And over time there has been a number of such LSH functions that have been designed. Right? And I need to show actually some of the classical things, right, that have been done. So suppose we want to hash documents, and one way to represent documents. So for example, we can embed these documents into Hamming space. And one way to do it is to have how do you obtain vectors in Hamming space of 0, 1s? So you'll take vectors where coordinates corresponds to words in this English dictionary, right? And the coordinate will be equal to 1 if that word appears in the document, and it will be 0 if it does not appear in the document. So this is kind of restriction to the words that we care about. So these different documents will be embedded in strings of Hamming strings, binary strings, and we can imagine computing the similarity between two strings by computing Hamming distance between these strings. So actually, the locality hashing was defined in this paper in Dikmatwani, and as I already showed, that the hash function here will be to choose this primitive hash function will be to choose a random coordinate. So here you choose some random coordinate and see if they're similar or not. So Manhattan distance, basically this is L1 distance, right? It's sum of the absolute values. So you might want to embed these documents not in binary strings, but perhaps in integer strings, meaning I might want to care about the plurality of the words, right? So if the word B appears many times, maybe I want to record a 2 here. So then the distance will be the difference, the sum of the differences from the coordinates. So here, something that we showed with Copenhagen in 2006 is some form of random grid that I showed for Euclid. This actually works here, and we'll achieve also 1/c exponent. So another very popular distance between sets is called Jacquard distance. It is essentially equal to the intersection of A and B divided by size of the intersection divided by size of the union of A and B. So you can think about these documents as being represented by sets of words, and you can compute the Jacquard distance between these sets. And one very well-known hash function introduced by Broder in 1997 called meanwise hashing. There is somebody talked about this. Mika, right? Okay, good. locality sensitive hashing actually, this hash function. So, there is some random permutation, so I won't go into detail here. There's also something called sin hash, which essentially corresponds to the distance between points being the angle between the 2 points. And there are many others that appear. And at least these work in Equantani together with the work of Broder, together with the work of Charikar, won this kind of Lattice Prize award for essentially introducing locality sensitive hashing. Yeah. So all of these obtain 1/c. Some of them work a little bit better if the points are sparse. So mean-wise hashing will actually work somewhat better if our vectors are sparse. But in theory, they all obtain 1/c. Okay? And here is what I promised to do is how do we choose approximation C? So I'm just, adding one more slide on saying, how LSH is used in practice, which is part of it. So in practice, oftentimes people are not okay with approximating the standard search. So approximation 2 might mean a lot of difference. So, what do we do, right? So as I mentioned, usually you'll use a locality sensitive hashing as a filtering mechanism, right? It will give you a list of candidates, hopefully much smaller than your entire database, and then you'll go through this list of candidates and filter out just the points that you need, the exact nearest neighbors. But then the question is, what shall I choose the approximation C to be? Right? I mean, I need to decide on C beforehand. Well, I mean, we don't really need to choose a C. We just need to choose these parameters L and K. And as long as, this formula is satisfied, we are guaranteed correctness. This formula will say that there is at most 10% chance that we will miss on a particular near neighbor. Okay? So you decide on, what's the probability that with which I'm okay, and then you can choose any KNL that satisfies this, right? And pictorially, to be some curve that looks something like that, right? That gives you some kind of trade-off between, as long as they're sufficiently large, then it's good, right? I mean, your safety is not guaranteed. Yeah, it's a trade-off, right? I mean, it's a trade-off between the number of tables and the number of false positives, right? So if you push L to be very high, you'll have less false positives, but then you'll have many hash tables, you'll spend a lot of time on hashing. If you choose L to be small, then you'll have fewer hash tables, but then you'll probably have more false positives. Okay, and one thing you can do is look at a particular data set and try to optimize this KNL for the particular data set. Okay, all right. So again, coming back to kind of theoretical statements and just giving a high-level perspective. In general, what I showed is not the only way to use locality sensitive hashing functions. There is actually some trade-offs, and so what I mentioned are exactly these trade-offs, right? That you can obtain space which is n to power rho 1 plus rho, time will be n to power rho, and for Hamming space we can obtain rho which is equal to 1/c, and for Euclidean space we can obtain rho which is equal to 1/c squared. So all these numbers will be for Euclidean space actually here. But there's out that you can trade off query time and space. So in particular, you can reduce space at the cost of increasing the query time. So you can push space to be roughly very close to n at the cost of having time which is n to power sigma. Now this sigma is something like also 1/c or 1/c squared, but with a higher constant. Okay, so if you really kind of tight on space, then you can increase the query time, and the really gist of the algorithm, or the difference of the algorithm, is that you construct much fewer hash tables, maybe just one hash table, but when you query, you don't query just one bucket. You query one bucket corresponding to the query, but also some nearby buckets. what exactly does it mean to be nearby buckets? You can imagine kind of looking at buckets which are touching my query in certain order, and you look at them. And this is really the algorithm, right? I mean, there are more details about how to choose these buckets, but you really will just sample more buckets from the same hash table. Okay? And these are the type of numbers that we can prove. There's also the other regime where instead you push the query time to be very low, and this will cost you in space now. And actually one of the, the same time with Inequantoni, there is a paper by Kuchev-Jostorovsky-Ramani who obtained time which was order d log n, which is really, really good. Right? This is logarithmic in n query time as opposed to polynomial in n. Except that the space becomes something like n to power 4 divided by epsilon squared for 1 plus epsilon approximation. Okay, so the query time is good, except that the space is really impractical here. Sorry, and yeah, so this is for approximation, let's say C less than 2. I mean, there are also some forms of these results for approximation bigger than 2. I didn't include them here. And at the same time, people have been thinking about lower bounds, right? So coming back to kind of the best partitions. These are questions, these are really kind of locally sensitive hashing functions are space partitions, right? And they do not talk about computation. And they are really mathematical objects. And people in functional analysis especially started looking, can we prove lower bounds? Are these best space partitions? And yes, starting with work by Motwani, Nawar Panigrahi, and later by O'Donnell, Wu, and Zhu, they showed that for locally sensitive hashing, as defined, rho should be at least 1 over C squared for Euclidean space, and should be at least 1 over C for Hamming space. So in particular, in the Motwani version of locally sensitive hashing is optimal. There is no other way to do better space partition in Hamming space. And the one that I showed you for Euclidean space is the best for Euclidean space. Okay? Now these are still kind of lower bounds about these objects, about these hash functions. Ideally would like to prove what are called self-probe lower bounds, data structure lower bounds. There is some work in this direction, though it's hard to prove very high query time lower bounds for self-probe. But what has been proven is that at least if you want space which is much less than n to power 1 plus small of 1 over C squared, then you need super constant number of memory lookups. The type of bounds here will actually look something like n to power 1 plus maybe order 1 over C squared divided by the number of, by T, which is the number of memory lookups. This is how these bounds look like. So it has been proven in this, of course we would like to prove that, this kind of space will require query time which is polynomial in n, but we are at the moment very far from that. Another interesting regime where such lower bounds have been proven, self-probe lower bounds, is that in this regime where the space is large and the query time is really, really small. So it says that if you want space much less than this amount, basically n to power constant divided by epsilon squared, then you need super constant number of memory lookups of self-probes. And I should say that these results actually, even if the time is d log n, it actually relies on one memory lookup into the data structure. So at least for constant number of memory lookups or self-probes, these type of algorithms are optimal. So at least this much we know. Okay, so this is the status. And it looks very close to, except for self-probe lower bounds, it looks like we're done here, right? It looks like, yes.
Well, I have a question about done.
Sorry?
I have a question about done.
Okay.
It's related to, there's a different family of data structures which have different incomparable guarantees.
Okay.
So there's this discovery tree that I worked on, but there's some other work. Essentially people assume some sort of dimensionality structure on
Right.
intrinsic dimensionality structure on
Right.
points.
Right.
And then given that you can get n space, you can get log n query time.
Right. question. So just to repeat what John mentioned is that there are, so what I'm talking here is about what we call high dimensional situations. So dimension D is really high, and we do not afford anything exponential in dimension D. There are many data structures that I did not mention here, and there's a lot of work on that, where the situation is considered to be low dimensional. Basically, we do afford things exponential in dimension D, either in query time or in space. And sometimes it's the ambient dimension, this dimension D, or it's the what is called intrinsic dimensions or doubling dimension, where you say that maybe data set has additional structure which essentially corresponds to a low dimensional structure. And the type of results look different there, but many of them are kind of exponential. Usually it's the query time, which will be something like 1 over epsilon to the power d. So the answer is that for some of these algorithms, you can prove that, like either taken as they are, or with some modifications, they actually also obtain guarantees in that regime.
So in general, all the items you talked about there aren't comparable, as far as you can tell, to who approved the cover tree.
So the type of guarantees that are proven here are incomparable, but some of the algorithms recover some of the algorithms in the low dimensional case. So some of these algorithms will, if the dimension is really small, or the intrinsic dimension is very small, some of the algorithms will actually run in query time, which is, you can prove that the algorithms will run in query time, which is something to power d. Right, so it begins to be a little bit comparable. So,
maybe this is something we should discuss later, but
sure.
I would like to see an algorithm which kind of get both of these, and I don't feel like we have that yet.
So some of these algorithms.
So, for example, if your points just happen to lie and have a small dimensionality, then it would be great if you get the same kind of guarantee you get the cover tree.
Some of these algorithms will, so for some of these algorithms you can prove that if the point set lies, say, in low dimensional subspace, then the query time will be smaller than say, root n. It will really be something exponential in dimension d, in this low dimensional space. So some of these algorithms, they might not recover the best type of guarantees for low dimensional spaces, but they do recover some values. Okay, so we can take this for fun. Okay. Okay, coming back to kind of the question of lower bounds, and are we done here? Is the only remaining thing to be proven here is to do self-prob lower bound? And the answer is no, actually. So it turns out, and this is something that I'm really excited, and as you can see, this is something like really kind of new. As in published this year. So it turns out that you can improve over locality sensitive hashing as defined by doing hashing which is data dependent. So these are still worst case bounds. There's still exactly the same theoretical guarantees, but it turns out that sometimes looking at the data set that we have at hand and designing and modifying the hash function as a function of this data set may give better query times. Okay? So in particular, for Hamming space, one can obtain query time which is roughly this space should be n to 1 plus rho. So n to power rho query time roughly, where rho is 7/8, something like 0.82, divided by c, as opposed to the optimal locality sensitive hashing for Hamming space is equal to 1 over c from init not 1 from n3. Okay? And essentially the same happens in Euclidean space. So one can obtain rho, which is roughly 7/8 divided by c squared, whereas the optimal SH here would be 1 over c squared. Okay? So what is this approximate? These are slightly ugly bound, but this is what we have at the moment. So this really, this is an improvement for sufficiently large C. Okay, the hope, of course, is, at some moment we should get this for, all possible values of C. But even for large values of C, this is an improvement essentially by 7/8 in the exponent. Right? So these are basically, these are polynomial improvements in the query time. And yeah, but the kind of by far the most surprising, what I find most surprising is that you can do hashing that is data dependent. Okay, so I'll try to describe this roughly in remaining 10 minutes. Just to give you a flavor of how these things look like and how can you do data dependent hashing. And but before that, let me describe, so there are LSH lower bounds, right? And there were very good indications that there is nothing else that can be done, right? So why do these lower bounds are not as predicted? So let me kind of give you a glimpse how these lower bounds look like. So, the actual lower bounds are based on Fourier analysis usually, and it's definitely beyond the scope of this lecture to describe them. But roughly, I'll tell you what are the hard distributions for these lower bounds, right? So the first paper essentially said like, okay, assume any distribution H over hash functions in Euclidean space, and the hard distribution essentially will generate a hard pair P and Q, which are random, and in Hamming space it will be roughly a distance d over 2. Closed pair will be P and Q random at distance d over 2 divided by C. Right? So we plant a query around a random point from the data set at distance d over 2 divided by C, so that we actually have exactly this ratio of C. And for this distribution, they proved that rho has to be at least half divided by C. Okay, so that was lower bound number 1. Then came O'Donnell, Wu, and Zhu, who said that, well, what we can do, we can improve this lower bound by taking slightly different distribution. So we'll generate P and Q at random, but we'll force them to be a distance roughly epsilon d. Okay? And the closed pair will be P and Q at distance epsilon d divided by C, where epsilon, think of this as very small constant. Okay? And for this distribution, you can prove that rho is at least 1 over C. Okay? So this is how this is the hard case for LSH. Okay? So now, why doesn't this transform into a good hard distribution for nearest neighbor? Well, the idea is that, so you try to generalize, so you try to extend this lower bound of LSH to actually nearest neighbor search, right? So how would you do it, right? So you pick a query point Q, you generate a closed point next to it, and then you have to generate a bunch, something like n-1 far points, right? All these far points have to be the distance roughly epsilon d by 2. Right, so for approximation it's equals to, let's say, right? So we generate a lot of far points at epsilon d. This is, okay, never mind that too. But what happens is that we have a query point Q. We generate a very nearby close point, right, the actual near neighbor, and then we generate a bunch of other points. So far points. Now what happens is that now the data structure takes the data set. This data set, you can see certain structure in this data set, namely that a lot of the points are concentrated in a certain ball. And there is exactly one point which is very close to the center of the ball, and this is our target near neighbor. So essentially, the data structure can look at this hard distribution that is generated and can see the structure. That all the points are kind of are concentrated in a ball. There is a point close to the center, so this point should be the close neighbor. So the thing is that essentially some LSH lower bounds that prove the optimal bound will have some additional structure that can be exploited. And the question is how to exploit such structure in general. Okay, so basically the algorithm will consist of 2 steps. One is to identify what are structures of the points that are useful for us, what are the structures of the points that will allow us a better hashing procedure, a better space partition. So there are certain configurations of points that somehow we manage to hash for which we have better space partitions. So this will be this nice geometric configuration, which will obtain rho which is less than 1 over c squared. And the second step, kind of for, I guess it should be the first step, is that we'll show how to take a general point set and reduce to this nice geometric configuration. Okay. So what is this nice configuration? Well, so this nice configuration is essentially the equivalent of sparsity. The Euclidean notion of sparsity. This is when the data set are as tightly packed in the space as possible. What does it mean? So we have a lot of the far points. So, I mean, we should require that the points are at distance roughly CR between themselves. So this is the far distance, right? And basically, so we have a lot of points at distance CR, distance at least CR between each other. How tightly can we pack these points? Well, we can, put them as tightly as possible on a sphere of radius roughly CR divided by root 2. There should be a picture. I'm not any. This is the picture. Ignore this for a moment. So this is the sphere, and basically, if you put a point here and you put a point here, then and this distance is CR, then the radius of this ball will be CR divided by root 2. Okay, this is the tightest possible packing. And it turns out that when our data set and the query point are all on this sphere, on the volume of this tightest possible sphere, we can obtain rho which is equal to half divided by c squared. Right? So there is a situation where we can obtain rho better than in general. And essentially the hashing procedure here is obtained, we call cup carving. It's a little bit similar to the ball carving kind of idea, except that you carve caps here. So basically you have this ball, you take a random line a certain distance from the center, and you carve out part of the space. Right? So you carve out part of the surface of this sphere, and then you repeat this a number of times. And again, if two caps intersect, then we have order, and the first cap that captures a point is the winner. And you do this until you've covered the entire surface of the sphere. Okay? As mentioned, this is similar to ball carving. And I'm not going to prove this, but you can obtain rho which is roughly half divided by c squared in this situation. Okay? And probably you want to prove a more robust version of here. It's like, okay, if what this here is not super tightly packed but a little bit more loose, so the radius is a little bit more, say eta times CR, then you can prove that rho essentially degrades slowly as you increase your radius. So in general, if you don't have any bound on the radius, then you'll have rho which is equal to 1 over c squared. But if you manage to tighten your point set, then you can get improvement in your exponent rho. Okay? So then, how do you reduce to this situation, right? So now you'd like to reduce to this situation where points are kind of tightly packed. And the idea is actually, to go back to LSH and use standard LSH to reduce to this case. And let's say the ball carving idea that I showed you earlier. So you think about this as applying a few rounds. So basically you apply LSH, but don't use, the K as predicted by theory, but use much smaller K. So basically we'll do only a coarse partition of the space. So we prepare as if the target approximation is something like 5C, right, as opposed to actual approximation C. What this achieves us is that LSH is naturally designed such that far points are unlikely to collide. So if we prepare for approximation, say 5C, then all the data is partitioned into buckets where the diameter should be roughly 5CR. Right? So LSH is such, so preparing for approximation 5C, this means that, again, 5 is an arbitrary number here, right? It doesn't matter that much. But you prepare for a bigger approximation, which means that you apply fewer rounds of this ball carving LSH. And what happens is that, well, LSH says, like, well, you prepare for approximation 5C, so the points at distance 5CR should not collide. Which is equivalent to say that my entire data set is partitioned into buckets or parts where the diameter of the point set should be roughly 5 CRs. And then you take these point set, you find the minimum closing ball, and now you are in this situation where you have a ball of radius roughly CR, maybe by a constant factor larger, and then you should be obtaining a row which is a little bit better than 1 versus square. Okay, and this is the entire equation. And let me just show you this pictorially. So again, we'll use n⁻⁻ hash tables, where each hash table will have a hash function. Now the hash function will essentially use a few functions h from the standard LSH, which is data independent. But after it has pre-partitioned the point sets a little bit, it will start using different hash functions which depend on the current partition. So pictorially, for example, at the beginning we do this ball carving. This is roughly how the coarse partition will look like. And then once we have pre-partitioned the point set using LSH, we will go inside, we will find these minimum closing balls, we'll tighten this here around the points, and then we will use this second LSH, which cap carving. And the data structure will be now, combination of a tree and a hash table. So first you have essentially a hash table according to this hash, first half of the prefix of the hash functions, which will pre-partition the data set into a few parts. And each of these parts will now use its own hash function, which depends on the actual points that are there, and have a second level of hash function. Okay, this is roughly how it looks. Okay, so, and you can think about the final row as being the average of the rows obtained in the first half and the second half, right? So the first half does not obtain a better row, it obtains 1 over c squared row. But the second half already obtains row which is less than 1 over c squared, so it's you can think about this as some kind of average between these two things, right? And, average between good and bad is, reasonably good. Okay, so there are details I'm going to skip in the interest of time. Yeah, let me talk a little bit about this slide. So practice of nearest neighbor search. Following some of the LSH ideas actually, so in practice there is a number of algorithms that are actually data dependent. So there is a number of trees, so okay, not all of them are data dependent, but many of them actually do use in practice this idea that I will partition the data set, the space partitions that depends on the data set. And for example, let me show you kind of how a PCA tree looks like. So it will take the data set, it will find what is called principal component analysis. So it will find a particular direction where the variance of the data is largest, and partition according to that direction, and then recurse on each part. So the theory of LSH will say, well, you shouldn't use the principal component or this biggest variance direction, you should use the random direction here. In practice, people say like, well, why should I choose random direction? Why shouldn't I choose a more specific direction that is better for my data set, and I'll choose this variance maximizing direction, and that's what we do, and oftentimes it works better. However, there is absolutely no guarantees that this gives you correct answers. And it's basically, for most of these algorithms, it's very easy to construct examples where it will fail to find your near neighbor, even with randomization. Okay? And there is very little theory, if any, about these data-dependent partitions and why they should help. So in some sense, there is a gap here, right? And it would be very nice to close this gap. So in some sense, what I've described is kind of one of the first steps towards this direction, where I mean, I personally found it surprising kind of that having hash function that depends on your data can improve in the worst case, for example. And I guess the best equivalent kind of in founder hashing would be perfect hashing, where you'll also hash and look at the size of the buckets to decide how to complete the hashing, right? So yeah, basically, actually just wanted to mention. So we have a very recent work that essentially shows that some of these algorithms work with sufficient randomization, even though we assume more about the data. So this is not completely worst case. Anyway, so just to complete the lecture, basically, what it was about is about localization hashing, which you should think about as hashing in a geometric setting, right? So this is state partitions, and something that is something very kind of recent and certainly not fully understood is that in this situation, at least, data-dependent hashing can do better than just pure hashing. The natural question is, can we do better upper bound? For example, it's natural that, the algorithm that I mentioned, it's natural to try to do it in multi-level, so you just do a little bit of hashing and then you maybe refocus on your balls, then you do a little bit more hashing, right? And it improves a little bit, but not much, I think from 0.8 to 0.7 or something like that. Most likely this is the right answer. It should be half divided by c squared, quick linear space, and we're applying that. And in general, kind of a bigger question is, what are the best space partitions or data-dependent space partitions in Fury in practice? And we'd like to close this gap, where in practice some data-dependent partitions do work better than random partitions data-independent, but we have no guarantees for that. And thing that I didn't mention, that we can do about LSH for our metrics like eddy distance, search over distance. Usually this goes by reducing these metrics to, say, Hamming space and then using LSH. We'd like to solve nearest neighbor search for many more distances. And another natural question is to prove lower bounds. Can we settle once and for all what is the right answer for nearest neighbor search in conditional space? Okay, and I'll end the lecture here.
Questions?
Lunch?
So when you say that this might be the right answer, do you think about C that is sufficiently big, or do you think even for C close to 1?
So the right bound should be half divided by C. Sorry.
So what if C is close to 1?
Yeah.
Do you think?
Yeah. So this is a bound stated for large C. The right answer should be something of the sort of 1 over 2c squared minus 1. So yeah, this is half divided by c squared is for large C. Other questions, or are we ready for?